Hello students, in this particular video we will do the insertion in a AVL tree. So as we understand that AVL tree is a special binary search tree in which the tree is balanced. That means all the leaves are at the same level. So let us draw one tree and make an insertion. So we have the node 50. It has the children 30 and 70. Then we have node 20, which is the left child, and node 40. This has a left child 10, and this has a, okay, this doesn't have a child, so this line is not there, and this has a right child 80. And now I want to insert into this tree value of 35. So first we will make the normal BST insertion, and then we will calculate the balancing factors. So first of all we will compare this 35 with 50. It is smaller, so we'll go to the left child. Then we will compare 35 with 30. It is larger, so we'll go to the right child of 30. Then we'll compare it with 40. The value of 35 is smaller, so we will add this node here like this, and the BST insertion is complete. Now what we have to do is we have to calculate the heights and the balancing factor, which is calculated from the height itself. So we know that the height of a leaf is 0, and the height of a null node, that means if the node is not there, some child is not there, then its height is -1. So let us follow this rule, and we will make use of this in this particular tree. So the height of 10 is 0, since it is a leaf. For 35 also the height is 0, and for 80 also the height is 0. Then the height of 20, it is from among its children, whatever is the largest value. Right child is -1, 10 is 0, 0 is larger, so 0 plus 1 will become 1. And here also the height will become 1. Here the height will become 1. These two children of 30 both have height of 1. So this is 1 plus 1, 2 height will be given to 30. 30 has a height of 2, 70 has a height of 1. So 50 will get a height of 3. Now we will find out the balancing factor. For balancing factor, we will find out the balancing factor of 20. So this 10 has a height of 0, and its right child is empty, so it is 0 minus -1. So plus 1 is the balancing factor of 20. Now for 40 we will calculate, so it is 0 minus -1, so it is again plus 1. Then for 70 it is 0 minus 1 for the left child, -1 minus 0, so it is -1, the balancing factor. Now we will calculate for 30. So 1 minus 1 will give us a value of 0, and then we will calculate for 50. So 2 minus 1 will give us 1. So as we can see, all the nodes, they have a balancing factor within 0, -1 and +1, which is a valid range, and therefore we do not need to rebalance the tree. Now in the same tree, let us insert a value of 36. So now we will insert 36 into the tree. So how the normal BST insertion will be made? So 50 is compared with 36. It is smaller, so left child. Then 30 is large hai. Then it is compared with 40, smaller. So with 35 it is larger. So this is the point where we will insert the node 36. Now let us calculate the heights. So this is 0, 0 and 0. This one is 1, 1, and this is 1. The height of 40 will become 2 now, and height of 30 is also 3, and the height of 50 will become 4. Right? If you do not understand how to calculate heights, I have recorded another video. You can refer to that video. So now the balancing factor. So for 20 the balancing factor is 0, that is the height of 10, minus the height of the null child, which is -1. So 0 minus -1. So we will get a height balancing factor of 1. Then for node 35, the balancing factor will be, this is 0, this one is -1, so -1 minus 0, will give us a value of -1. 35 has a balancing factor of -1. Now we will calculate the balancing factor of 40. So this has a left child with a height of 1, right child with a height of -1. So this will become 1 minus minus 1. Why we are doing minus minus? Because the height of the left subtree minus the height of the right subtree. Here the right subtree is empty, so it is -1, and therefore what we are getting is this minus minus will become plus, so height of 40 will become 2, and the allowed range of balancing factors is 0, -1 and +1. So this range is violated, and therefore this particular subtree is imbalanced because the balancing factor of 40 is 2. So what we will do, we will mark this here. This is a left right case. So first we have to perform a left rotation, and then we will perform a right rotation. So what is the case here? We have a Z, we have a Y, and we have a X. So first we will left rotate the Y. So Y will become a child of X, and then we will right rotate Z, and Z will become the right child of X. So this thing when we will perform here, 36 will become the root, then the node 35 will become its left child, and 40 will become its right child. So when I make this change in this particular tree, I will get a value of 50. Then at the base we will have 30 and 70. Here 80 is there. Now 30 has two children, it has child 20, and now instead of 40 I will write 36, and here 35 is there, here 40, and here we have 10. So this is the new tree after the balancing. So you can see here clearly that how the trees have been transformed after the insertion of 36. So all the cases of the insertion, there are 4 cases. There is a left case, there is a right case, there is a left case, and there is a right case. In case of left only one right rotation is required. In case of right only one left rotation is required. And in case of left first left rotation and then the right rotation is required, and in the right first the right rotation and then the left rotation is required. I have recorded another video in which the AVL rotations and with the XYZ are explained, so you can refer to that video. Thank you very much for watching.